Alright, today we're going to work with trigonometric integrals and more importantly, somewhat more complex trigonometric integrals than what we've been working with. Okay, and our objective is going to be solve trig integrals involving powers of sine and cosine, involving powers of secant and tangent, and then involving sine-cosine products with different angles. Okay, this is going to be, I'm going to split this into two different videos. We'll address the sine and cosine integrals first, then we'll do secant and tangent. Alright, so for integrals in these forms, where we have sine to some power m x, cosine to some power n of x dx, and secant to some power m of x, tangent to some power of n of x dx, where m or n is a positive integer, we can solve these problems by breaking them into combinations of trigonometric integrals to which we can apply the power rule. So for example, let's say I have something like sine to the fifth of x cosine of x dx. What you can do here is just recognize or let u be sine of x, and then we can rewrite sine to the fifth of x, that's the same as sine of x to the fifth, or u to the fifth. And then you would recognize that du, well, the derivative of sine is cosine of x dx. And then you recognize that this is the same thing as saying u to the fifth times du once you substitute those things in. And then basically that's just a power rule. Do the antiderivative of u to the fifth, add 1 to the exponent, that's u to the sixth, divide by that same power, u to the 6 over 6. It's a indefinite integral, so plus c. Plug back in your u value, you're going to find that this equals sine of 6 of x, sine to the 6th of x, over 6 plus c. So basically what we're going to be doing is trying to do some properties and then just basically apply a power rule here with these trigs and effectively get rid of either a cosine or a sine, or get rid of a tangent or a secant. We'll talk about that in a little bit. And we're going to have to use some trig identities as well. So some important identities are going to be the Pythagorean identities. So we're going to be working first with sine and cosine in this video. So the Pythagorean identity, these are all on your cheat sheet. I'd encourage you to check that out. Is going to be, well, sine squared of x plus cosine squared of x equals 1. That's a Pythagorean identity. I want to make sure I have my drawing stuff up here. That's a Pythagorean identity. And then we're also going to be using half-angle identities and kind of an application of them. They're not going to look exactly the same as the ones in your trig cheat sheet, but they're just going to be almost the exact same, just written a little differently. So we know that sine squared of x using a half-angle identity is the same thing as, well, 1/2 times negative cosine of 2x, or that's the same as 1 minus cosine of 2x over 2. And cosine squared of x is going to equal 1 plus cosine of 2x over 2. Okay, so we'll be going over some guidelines to evaluate integrals involving sine and cosine, and they're going to involve these identities. I guess I should write that these are half-angle identities. Half-angle, let's make that legible. Half-angle identities. Okay, and we're going to use these guidelines and basically just try to move these around so we can apply a power rule, and then we're going to have to use some trig identities to do that. So here are some guidelines. I write these, but I'd encourage you to pause the video and write these down. So we have these three guidelines when we're trying to involve sine and cosine. If the power of sine is odd and positive, we want to save one sine factor and convert the remaining factors to cosines. Then we're going to expand and integrate. So what that means is if we have sine to some 2x plus 1, some value, or I'm going to change this to k. This should be k. 2 times k plus 1 of x times cosine to the n of x, where the exponent of sine is odd and positive. What we want to do is kind of break this up into one sine, into some sine factors, into one sine factor, and convert the remaining factors to cosines. So we can write this as sine squared of x to the k times cosine to the n of x times sine of x dx. Okay, now our goal here is to convert this sine, I guess I'll use a different color. We want to convert this to cosine, and if we convert that to cosine, then we can basically let that be our u. If cosine is our u, well, what is our du? And our du will be sine. So this effectively becomes our du. Okay, but we want to get everything in terms of cosine. So we have one last step. We have to use that half angle identity here. We know that sine squared of x is the same as 1 minus not the half angle identity. This would be a Pythagorean identity. This is 1 minus cosine squared of x to the k times cosine to the n of x sine of x dx. Okay, and then we can integrate that basically by recognizing some power rules there. However, if we have the power of cosine is odd, so basically the same case but with cosine, if the power of cosine is odd and positive, we want to save one cosine factor, then convert the remaining factors to be in terms of sines, then expand and integrate. So sine to the m times cosine to the 2k plus 1. Now our exponent for cosine is odd and positive. We want to convert our cosines to sines, but then also save one cosine factor because that will become our du. So this is going to be the same as the integral of, sine to the m of x. That's the same. Then we are going to basically factor out a cosine, and that's going to leave, when we factor out a single cosine, we're left with cosine squared of x to the k. And then we factor out a cosine. That's the same as cosine to the x. Okay, the reason this is the same thing is, cosine to the x times cosine squared x to the k, that's like to the 2k times cosine of x, that's 2k plus 1 more cosine, which is how we would get here, cosine 2k plus 1. So we're basically just factoring out a cosine, one cosine factor, and then converting whatever we have left to be in terms of sines. So we're going to convert this cosine squared of x, convert that to sines. And then when we do that, our sine is going to be our u, and then our du is going to be cosine of x. Or some form of du. I guess up here, the derivative of cosine is technically negative sine, so we have to keep that in mind. I'm going to write du-ish. That's a super official term. Okay. And then, we want to convert everything in terms of, when we're doing down here in guideline 2, these cosines, we want them as sines, so apply a Pythagorean identity. This is the same as the integral of sine to the m of x, whatever power that is, times that Pythagorean identity tells me cosine squared of x is the same as 1 minus sine squared of x to the k, and then times cosine of x dx. Then we can apply the power rule and kind of integrate there. Now, the third guideline, however, if the powers of both sine and cosine are even, or we're just basically saying if we don't have an odd positive exponent for either sine or cosine, we have to make repeated use of these identities, kind of an application of the half angle identity. Sine squared of x is going to equal 1 minus cosine of 2x over 2. And cosine squared of x is going to be 1 plus cosine of 2x over 2. Okay, so if both the powers of sine and cosine are even and non-negative, make repeated use of the identities. Sine squared of x equals this, and cosine squared of x equals 1 plus cosine of 2x over 2. And to convert the integrand to odd powers of cosine. So once we get them to have odd powers, then we can keep going as if it was, guideline 2 or maybe guideline 1, whichever one it is. So basically get them to have odd powers and then repeat those processes. Okay, so make sure you have that written down. We're going to move to an example. Okay, and it basically tells us what's going on here, but you should recognize, I have sine cubed of x, or sine of x to the third. We know that our sine power is going to be odd. This is going to be guideline number 1, which means when we have an odd and positive sine of, or power of the sine, what we want to do is basically get everything to be in terms of cosine, leave one sine, and then apply some power rules, okay? So, following step 1, we basically want to get everything in terms of cosine and leave one power of sine. So we're going to factor out a sine here. This is the same as sine, if I factor out a sine, this is the same as sine squared of x cosine to the fourth of x times sine of x dx. I've just factored out that sine of x here, okay? And then I'm doing the integral of this. And that's going to equal, okay, now we want to get this sine The single sign we leave alone because that's going to be our du essentially. The sine squared, we want to get that in terms of cosine, so use a Pythagorean identity. That's the same as 1 minus cosine squared of x. Okay, what I just did there, that's just a Pythagorean identity. And we're multiplying that still by cosine to the 4th of x sine of x dx. Our end goal when we see something like this is to get it in the form where we have cosine of u, I guess not cosine of u, I guess cosine of something like cosine of x to some power times sine of x dx. Basically, you want to get our u is going to be cosine of x and our du is going to equal negative sine of x. You want to get it to look something like cosine times sine. Okay, I'm going to erase that, but that's what we're trying to do here. So what we want to do then is we want everything to be like cosine times sine. So we're going to distribute this cosine to the 4th here. This is going to be cosine to the 4th times 1 gives me cosine to the 4th of x minus cosine squared of x times cosine to the 4th of x gives us cosine to the 6th of x. And we're multiplying that by sine of x dx. Remember, our goal here is to get everything so it's like cosine sine, so we can apply the power rule. Well, this is going to be then the integral of cosine to the 4th of x times sine of x minus the integral of cosine to the 6th of x times sine of x. And then I need a dx here. Okay, well, how does this help us? So essentially, this point, we have a cosine times a sine. We can recognize that our u is going to be cosine of x. Our du then becomes negative sine of x. That's what we want. Okay, now we're very close with that. We almost have cosine times a negative sine, but we have a positive sign here. So what we have to do is just rewrite this. So this is actually our du, which we want to be negative sine. This is going to be, well, to get this to be negative sine and without changing the value of this integral, we know we have to multiply by a negative out front as well. So this is negative cosine to the 4th of x times negative sine of x dx minus, okay, and we're going to have to do the same thing here since this sign is positive. Well, minus cosine to the 6th of x times negative sine of x dx. And since I changed this to a negative, I have to multiply by negative 1. And, well, a negative times a negative. This is just going to be a positive plus that integral of cosine to the 6th of x times negative sine of x dx. Okay. And I guess I'm just going to clearly show, well, this basically is your u. This becomes your du. If you want to work this out, this is like having just this one right here that I'm going to highlight in yellow, or I'll highlight it in blue, right here. If we were to do this on the side, I'm not going to show my work in both of these integrals, but basically what we're doing is, well, if u is cosine of x, then this integral in blue becomes negative integral of u to the 5th, and then our du, well, if u is cosine of x, then du is negative sine of x dx, which we have right there. So this just becomes u to the, I guess, before we evaluate, u to the 4th of du, and the power rule just tells me I'm going to add 1 to the exponent. This becomes negative out front times add 1 to the exponent, u to the 5th, divide by that, and then plus c. So that's really what's going on here. Okay, so I know that the antiderivative of this is just going to be, well, this value, add 1 to the exponent. It's going to be cosine to the 5th of x, then divide by that value, and I still have a negative out front. Okay, plus, this is going to be u to the 6th, technically, u to the 6th du, which we're going to add 1 to that exponent. It's going to be plus u to the 7th, or our u is cosine of x to the 7th. Over 7, and I guess I should put that in parentheses, or I should just write it instead as cosine of to the 7th of x over 7 plus c. So basically, and that's all that one's going to take, what we want to do here is basically get it so it looks like something that we can apply the power rule for. Now, that was if sine is odd and positive. We're going to work through an example where cosine is odd and positive. It's going to be the exact same type of thing. You're going to want to convert everything in terms of whatever you want that u to be, and then leave something that looks like that du, and then integrate. So when the power of cosine is odd, well, if you look here, what about this square root of sine of x? Okay, now, that might seem like it would throw us off, but really, this is what we want. Since the cosine of x is being raised to the third power, since it has an odd positive thing, we're going to look at, well, rule number 2, which tells us that we want to get everything in terms of sine and then leave one cosine. This is going to be guideline 2. And what we want to do is just rewrite this integral. Technically, my power of sine of x is negative 1/2. But since we're only concerned with the power of cosine here, it's going to meet the cases that it needs to for us to follow guideline 2. That's not going to be a problem for us. The fact that it has a negative rational exponent isn't going to be a problem. So we can rewrite this technically if you want as, well, the integral from pi over 6 to pi over 3, this definite integral of cosine cubed of x. Before you even get anywhere, you can write that as cosine cubed of x times sine of x to the negative 1/2 dx. We're just rewriting the way that looks. And then we can start applying, I'm going to move my work way over there. We can start applying that guideline, which tells us we want to factor out a single cosine and then convert everything to sine. That's what it tells us to do in guideline 2 number there. So convert everything to sine, leave one cosine, that will become our du. And then we are going to integrate. So basically, when our cosine has an odd power, we know our u is going to equal sine of x, our du equals cosine of x. That's why we leave a single cosine of x. When up here, however, when our sine is odd, then we know that our u is going to equal cosine of x, and our du is going to equal negative sine of x dx. I need a dx down here as well. So they're very similar rules, just kind of flipped. All right, so we want to get this cosine cubed of x right here. We want to factor out a single cosine and leave the rest. So if I factor out a single cosine, this is just going to be, well, this is going to be the integral, definite integral, pi over 6 to pi over 3 of cosine squared of x, once I factor that out. And then that's going to be still times sine of x to the negative 1/2. And I factor out a cosine x, I'm left with cosine x dx. And this effectively becomes our du and our sine. After we convert it, I guess I should have waited. After we convert it, that's going to be our u. Okay, so get everything in terms of sine other than that single cosine we factored out. This is going to be pi over 6 to pi over 3. And we know that cosine squared of x, we use a Pythagorean theorem, or Pythagorean identity. We know that cosine squared of x is going to equal 1 minus sine squared of x times sine of x to the negative 1/2 times cosine of x dx. Now this might be where I want to highlight. This is essentially if u equals sine of x, then du, that implies that du is going to equal, well, derivative of sine is cosine of x dx right here. So this is our du. Okay, but we want to get everything to look like it's sine of x. We want it to be u du, so we want it to be sine of x times cosine of x. So again, we're going to have to distribute the sine of x here. This is going to be equal to pi over 6 to pi over 3. Well, sine of x to the negative 1/2 times 1 just gives me sine of x to the negative 1/2. Minus sine squared of x times sine of x to the negative 1/2. Remember, when you're multiplying powers with the same base, you add their exponents. So sine squared of x times sine x to the negative 1/2 is going to be, I need this in parentheses, is going to be equal to, well, 2 plus negative 1/2 gives me 3/2. So this is going to be sine of x to the negative 1/2. And I'm still multiplying by that cosine of x here. So times cosine of x plus, or I guess I should say minus, and then we're going to distribute here. Well, sine squared of x times sine of x to the 1/2 gives me, add those exponents, this should be negative 1/2. That kind of isn't very clear. So 2 plus negative 1/2 gives me 3/2. That's going to be minus sine of x to the negative, or to the positive 3/2, excuse me, to the positive 3/2 x, yeah, that's fine, times cosine of x dx. Okay. And I'm actually going to use brackets to make it a little bit more clear here. So our goal is basically to get everything to be sine of x times cosine of x, because remember our u is going to be sine of x, which implies our du is going to be cosine of x. Okay, so this essentially just becomes, if I want to rewrite this up in this margin here, this is the same as the integral from whatever to whatever. This is going to be u to the negative 1/2 times, well, our du. This is going to be u to the 3/2 times du. Remember that there's this dx being multiplied technically to each of these. Because if u is sine of x, well, this is going to be negative u, I guess. Negative integral of u to the 3/2 du. So we got it to look like that, and now we can just apply the power rule here. So we're going to do the antiderivative of sine of x to the negative 1/2 cosine of x. Well, that's like doing u to the negative 1/2 times du. So we just add 1 to that exponent. Well, negative 1/2 plus 1, that's just going to be u to the 1/2 divided by 1/2. And remember, our u is sine of x. So this is just like sine of x to the 1/2. Add 1 to that power up here. And then divide by that, divided by 1/2. Okay, and then we're subtracting, well, u to the 3/2, again, we're going to add 1 to that exponent, so that's going to be u to the 5/2, but u is sine of x, so sine of x to the 5/2 divided by that quantity, divided by 5/2. And we're doing a definite integral here, so we're evaluating this from pi over 6 to pi over 3. Okay, plug that in. You're going to find that you're going to get approximately, if you round, about 0.239. And that is going to be the value of this integral. That's the area bounded by this region from pi to 6, or from pi over 6 to pi over 3. So in these examples, the first and second one we did, basically recognize what guideline you're going to want to use, and then you want to just get it so it's in terms of u du, whatever the case might be. Get it in terms of u du, apply the power rule there. Okay, and you can only use these if either the power of cosine is odd or the power of sine is odd. And I guess I should say odd and positive. So if the power of sine or cosine is odd and positive, you can use these rules. However, if you come to an example where neither of those are odd or positive, like for example, or like I guess I should say just they're not odd. So if neither your sine or cosine is odd, you're going to want to, well, maybe use guideline 3. So if you have even and non-negative powers like we do in example 3, this is where the half angle identities are going to come into play. And then basically from there, we're going to kind of rework it as if it was similar to the examples we just did. So since m and n, remember that m and n represent our powers for sine and cosine. Since m and n are both even / non-negative, and you might be thinking, well, m doesn't exist. There is no exponent for sine. Technically there is. That value for m is technically what? 0. And 0 is an even number. 0 is an even number. It's not positive or negative. It's just, it's non-negative, and it is even. So since both m and n are even and non-negative, we can replace, basically we're going to use those half angle identities. And we can replace cosine to the 4x, cosine to the 4 of x, by, well, we know that cosine squared of x is going to be 1 plus cosine 2 of x over 2. So if I have cosine to the 4th of x, that's the same as saying, well, 1 plus cosine of 2x over 2 squared. Okay, so we're just going to start by rewriting this integral. We know that the integral of cosine of to the 4th of x, or cosine of x to the 4th, dx. That's the same as the integral of 1 plus cosine of 2x over 2 squared dx. Okay, now how is that helpful? Basically what you're going to kind of want to do is, again, break apart that fraction like we've done in examples previous. We can write this, and then I guess you also kind of want to expand that numerator. Well, 1 plus cosine of 2x, if I square that value, well, 1 times 1 gives me 1. Okay, then I'm going to have a cosine of 2x times 1 plus another cosine of 2x plus 1. That gives me 2 cosine of 2x. And then cosine of 2x times cosine of 2x will give me cosine squared of 2x. So we're just expanding, we're squaring that numerator. And then we're going to square the denominator. 2 squared is 4. So basically we're squaring this binomial, squaring this 2, and we're getting here this integral. Okay, now that seems pretty complicated. What we're going to do is just break up this integral. This is the same as 1 over 4, so the integral of 1 over 4, plus the integral of 2 cosine of 2x over 4. And you know what? I don't want to break up the integrals just yet. I'm just going to split up this fraction. This is the same as doing the integral of 1/4 plus 2 cosine of 2x over 4. Well, that's just going to reduce 2 divided by 4. That's the same as cosine of 2x over 2 plus cosine squared of 2x over 4 dx. All right, so, well, the 1/4, that one's going to be pretty easy to tackle. Cosine of 2x over 2. Okay, we're going to kind of ignore the denominator. That's the same as multiplying by constant of 1/2. How do I do the antiderivative of cosine of 2x? How do I do the antiderivative of cosine of 2x? Remember that this 2x is technically the inside. This is the inside. So it's kind of like a chain rule, reversing a chain rule. We're going to have to think of it like reversing a chain rule. So you should see that this should be the derivative of the inside, which would be just 2 times, well, the derivative of the outside. Remember, the chain rule is derivative of the outside with respect to the inside times the derivative of the inside. So we're basically going to be reversing a chain rule here and here. And we'll get to that in just a little bit, okay? So what we can do is further simplify this. You can pull out your factors. This is the same as the integral of 1/4, we'll leave that, plus 1/2 times cosine of 2x plus 1/4 times, and simultaneously, we know that cosine squared of 2x, if we apply that half angle identity, we know that cosine squared of x is equal to 1 plus cosine of 2x over 2. So if we have the cosine squared of 2x, that should be equal to 1 plus cosine of 4x over 2. So we're going to apply that half angle rule. This is 1 plus cosine of, well, it would normally be 2x if it was just a single x, but we have 2 x's, so multiply that by that. So we get cosine of 4x over 2. So we kind of did two things there in this one here, in this cosine squared of 2x over 4. We first factored out that constant, or I guess, yeah, that 1/4, and then we just rewrote it using that half angle identity. Okay. So, here's where we get a little work involved, and I'm writing quite large. I'm not leaving myself a whole lot of room here. What we want to do here is, again, we're doing the integral of all of this. That's the same as doing the integral of each of these things individually. Well, we have this constant 1/4, and we have technically a fraction that we can split up even further. This 1 plus cosine of 4x, I can split that into 1/2, and then I can split that into cosine, I guess 1/2 plus cosine of 4x over 2. So we're going to have some things to rewrite here. This is the same as the integral of 1/4 plus, well, we're going to have, and this is where the power rule comes into play here. and I'm going to actually split these up. This is 1/4 dx plus, okay, this would be 1/2 times the integral of cosine of 2x dx. Now we're thinking about what is the antiderivative of cosine of 2x. Okay, and this is the form cosine of u. And remember that if I was doing the derivative of something, basically we're saying what derivative gives us cosine of something. Well, we know that sine's derivative is cosine, but we know that sine of u is technically, if u is just not a single variable, sine of u is equal to cosine of u du times the derivative of the inside. That's kind of like a chain rule application, remember? So the derivative of sine of u is technically the derivative of the outside, the derivative of the outside, which is just sine. Well, we know that derivative of sine is cosine, with respect to the inside, u, times the derivative of the inside. So we're basically saying, well, this is kind of like having sine of 2x. This is kind of like having sine of 2x, but remember that this should be being multiplied by the derivative of the inside, so we should be seeing a 2 here. Okay, now we can reverse that. But if I don't want to change the value of this, I technically have to multiply by 1/2 again. Okay, so we're kind of reversing a chain rule here in that one. And then we're still adding, well, 1/4. We're going to have 1/4, and I'm going to also break up this fraction. This 1 plus cosine of 4x over 2 is the same as 1/2 times 1/2 plus cosine of 4x over 2. Okay, well, this is going to be the same as 1/4 times 1/2. 1/4 times 1/2 is 1/8. So this is the same as the integral of 1/8 plus the integral of well, if we have cosine of 4x over 2, that's the same as 1/2 times cosine of 4x. And we're going to have to do a similar thing that we did over here. It's going to be like reversing the chain rule. It's like if we had sine of 4x, but if we were doing the derivative of sine of 4x, we should technically have a 4 here. So what do I have to multiply to keep that? You have to multiply by 1/4. All right, so this is a lot going on here. There's a lot going on here. So what we're going to have is and hold on, I need to double check my math here. Okay, we're good here. What we want to do is we have a 1/4, and I guess I forgot my dx's here. We have a 1/4 and a 1/8. We can add those together. 1/4 plus 1/8 is the same as 2/8 plus 1/8, which gives me 3/8. This is the same as the integral of 3/8, and this is where it's going to get cleaned up a little bit. This is the same as 3/8 dx plus, well, 1/2 times 1/2, that's the same as 1/4 times the integral of 2 cosine of 2x dx plus, we got rid of this 1/8, we added that to the 1/4, so we're done with that, plus 1/2 times 1/4, 1/2 times 1/4, and I also forgot to distribute this 1/4. So we have this 1/4 times this cosine of 4x over 2. So technically it should be 1/2 times 1/4 times 1/4 again. That's going to give us 2 times 4 gives us 32. So 1/32 of 4 cosine 4x. Again, that 1/4, the reason I had to rewrite that is because we first factored out this 1/2 here. It would have been cosine of 4x over 2, factored out that 1/2. We have that 1/4 just by rewriting it. That way we can kind of reverse the chain rule here. And then I still have that 1/4 that's being multiplied when I did that there. So that's where that came from. I forgot to write that. But this is going to be 1/32 times 4 cosine of 4x. And then I need my dx here. So let's evaluate this integral. Okay, well, the antiderivative of 3/8, that's easy enough to do. That's just 3/8 x. The antiderivative of, well, we're going to have 1/4 times the antiderivative of 2 cosine of 2x. we have rewritten this, so it's basically like reversing the chain rule. Keep in mind, we see basically this. We see the derivative of the inside being multiplied by the outside. You should recognize this is a chain rule. And the antiderivative of 2 cosine of 2x, well, that's just going to be, we're saying what derivative gives me 2 cosine of 2x? And the answer is sine of 2x. And you can check that. If I were to do the derivative of sine of 2x, it's like doing the derivative of the outside with respect to the inside times the derivative of the inside. That's the same as doing, well, the derivative of sine of 2x is going to be cosine of 2x times the derivative of the inside would just be 2. So it would be cosine of 2x times 2, or 2 cosine of 2x. So we're just reversing that. Okay, plus 1/32, and this is going to follow the same suit. 4 cosine of 4x, the antiderivative of that is again going to be sine of, well, 4x. And then these are all indefinite integrals. We're going to have our plus c here. So we have 3/8 x plus 1/4 sine of 2x plus 1/32 times sine of 4x plus c. If you want to write these fractions and just put everything in the numerator, that's fine, but this is also perfectly acceptable. So this is what you kind of want to do if you have powers of cosine and sine that are even and non-negative. You want to rewrite them kind of using those half-angle identities. Okay. So in the example above, if we were to evaluate the definite integral from 0 to pi over 2, we would obtain 0 to pi over 2 cosine to the n of x dx, and I guess I want to write this as the fourth, so it's our example. We'd get the same thing here, but we would be evaluating it. So it would be, I wonder if I could make a copy. And let's copy that and paste it here. Whoa. Nice. Okay, so, but if we were doing a definite integral, we wouldn't have that c. We'd be evaluating from 0 to pi over 2. And that would be equal to, well, if you plug that in, you would get 3 pi over 16 plus 0 minus if we did the lower limit of integration, and you would just plug in 0, which means you'd get 0 a bunch of times. Really what we're getting here, the only term contributing to the solution would be that 3/8 x, or 3x over 8. Okay, we can generalize this in Wallace's formula, which can kind of come in handy when you're doing definite integrals and you don't want to actually do them. It states that if the degree n of something is odd, for this cosine here, then, well, 0 to pi over 2 of cosine of n of x dx is equal to 2/3 times 4/5 times 6/7 times ... so on and so forth, till you get to whatever that value of n minus 1 is over that value of n. So basically, if you look here, you notice that you're just multiplying a fraction 2/3 times you add 2 to the numerator and denominator all the way until you get to the value in the denominator that's equal to your degree. So if n is even, if n is greater than 2, you have to have these rules. Then 0 to pi over 2 cosine to the n of dx equals 1/2 times 3/4 times 5/6 times ... so on and so forth, till you get to n minus 1 over n times pi over 2. So for example, if we were to just rewrite this right here, using Wallace's formula, well, if I'm going from 0 to pi over 2 of cosine to the 4 of x dx, well, my n value would be 4. It's even, and it's greater than or equal to 2, which tells me, well, by Wallace's formula, we know that the definite integral is going to be the same as doing 1/2 times add 1 to the numerator and denominator until my denominator becomes the same value as my exponent. Well, this is going to be 3/4, and I've essentially gotten to the point, not essentially, I have gotten to the point where my denominator is the same as my exponent. And since it's even, I have to multiply by this pi over 2, and I would just get, well, 3 pi over 2 times 4 times 2 is 16, which is what we got. Oh, whoops, I didn't even evaluate that. That's what we would have got here. if I just added all those zeros. 3 pi over 16. So you can kind of use Wallace's formula as a shortcut if you have something in that structure. Okay, that's going to be all we work with in this section, at least this part of the notes. That's our sine and cosine section. The next section we're going to be working with secant and tangent. All right, have a good day, everybody, and as always, stay safe out there.